Okay. Okay, let's get started. Before starting today's class, so as I announced, I announced regarding the final exam logistics on LMS. Okay, so you can find so we will take the final exam on June 19th, June 19th, right? Okay, and then like the midterm exam, we will take the final exam during the regular class time, but I think it will end slightly later. So so it can end at 11:55, but so it can be extended, right? So if someone will take the exam in the next class time, right? I believe usually the next class will start at uh, 12, right? But so usually it's a lunchtime, but so some classes can start at 12. So if you have any concerns or the time schedule conflict, then let me know quickly, okay? So you can email me, okay? Uh, so the final exam is the also the closed book exam, and then so it will cover chapters 4, 5, and 6 of the textbook, right? So and that's it. So you can use a simple calculator, okay? But you cannot use any electric devices, okay? So any question about the final exam? So okay. And then unfortunately, so we cannot have in-person lectures for upcoming 3 classes. Okay, so because I need to attend the conference in the United States, so we cannot have in-person lectures. So I will record the lectures, and then I will post the recorded lectures on YouTube, right? And then also the last class. So the last class is in the on the June 17th, right? And then so I will also provide the recorded lecture for the last class. It is because the it's the final exam week. So I think the students uh, can prepare for some final exams of other classes, other courses, right? So I will provide. So I plan to post the last lecture on June 14th, right? So actually, I need to record the lecture during my uh, business trip. Okay. But anyway, so I provide the recorded lecture for upcoming, actually 4 classes, because we missed 1 class because of Labor Day. Okay, so I will post the 4 lectures. Okay, I will post the 4 recorded lectures after this class. Okay. Okay. Sorry for your inconvenience, but okay. So okay. So I will. So let's start today's class. Okay. So in the previous class, we learned about the cache organization. Okay, so we learned about the basic concept of a cache, and then so we will learn about the cache mapping. So this cache mapping scheme is called a direct map. So this cache is called a direct mapped cache because so as we learned the in the direct mapped cache we use the part of the addresses. So we use the part of address as the cache indexes. Okay. So in this example, the cache includes the the 1024 blocks, right? So you can find the cache entries, and then each entry includes the data field, and then also tag field, and then valid field, right? So this is the one cache entry, and then so so this cache includes the 1024 cache blocks, or so I mentioned that we can call a cache block as for cache block. Also, the we can call the cache line, right? We can call it a cache line. Okay, so this cache includes the 1024 cache lines, and it means we can use the 10 bits of index bit, right? So in order to identify each entry of the cache block, so we can use the 10 bit of index. So index field includes the 10 bits. So we can use this 10 bits from the address field, address bits, right? Because we can access the memory using the address. So which means we can also access the cache using the address. Okay. So, but in order to identify the target cache block, so we can use the part of the address bits, right? So we use the 10 bits for this example. Also, so you need to also understand about the cache block size. So cache block size represents the size of data that can be stored in a single cache entry or a single cache block. So in this example, so you can find the byte offset field. So this byte offset field includes the 2 bits. So what does that mean? Each cache entry or each cache block can store this amount of data. So using the 2 bits of the address bit, we can represent the 4 byte, right? So because it's a 2 bit. So it means for this cache, the line size, or it's also called a block size. The block size of this cache is 4 byte. So which means one cache entry can store 4 byte of data, right? So here, so you need to understand the cache organization based on some address bits, and then which bits are mapped to the index field, also byte offset field of the cache. Okay. So also we can adjust the size of a cache block. So actually in this example, the size of a single cache block is 4 byte, but we can increase the size. So in this example, the cache block size is 16 byte. Okay, so we can adjust. So when we apply this 16 byte of cache block, then the byte offset field will be increased. So it is because in order to represent the 16 byte of the block, so we require 4 bits, right? So the offset field, the byte offset field will occupy the 4 bits in the address field. Okay, also in this example, the cache block, the number of cache blocks is 64, right? So in order to represent 64 blocks, we require 6 bit because 2 to the power of 6 is 64. So we can use the next 6 bits for the cache index. Then the remaining bits are tags, right? So as I mentioned, we require address to identify data. But so within this address, we can use this amount of bits for representing index and the byte offset. So we don't require this information, right? So we just store the remaining bits. the remaining bits for tag. Okay, so as you can see, the tag is stored in this field of the cache. Okay, so when we access the cache, firstly we just identify index from the address field, right? So using this index, we access the cache. Then we can check the valid bit and tag, right? If the valid bit is 1, so it means that the target cache entry includes a valid data or valid data block. And then we need to also compare the tag, right? So which means we need to check if the target cache line includes the requested data, right? So we need to compare the tag with the tag field of the address. So if the valid bit is 1, and then if the tag is matched to the tag field of the address, then it's 1, then it means, oh, this cache includes the requested data. So which means it's cache hit. It's a cache hit. Then cache can provide this data to the CPU, right? So we can also we can calculate the block address like this with this uh, equation, right? So and then so we can just so if this is the address, and then we can just divide the address using the cache block size. So which means we can just identify the the block the block address, right? Then we in order to identify the block number, then we can just perform modulo operation. So this block address is the divided by 64. So that is the number of blocks, and but this is the modular operation. So we can calculate the the index of the cache. And then I also mentioned that usually in a commodity CPU, the cache block size is larger. Okay, so actually in a commodity CPUs, the cache block size is usually 64 bytes, right? And then actually this 64, this number is determined by the characteristics of DRAM, right? It is related to the burst length of DRAM access, but we will not cover about the DRAM in this course. So you can just remember that usually in a commodity CPU, the cache block size is determined by the DRAM, okay? The characteristics of DRAM, okay? And then usually this is 64 bytes, okay? So anyway, in this example, the cache block size is 4 bytes. And then in this example, the cache block size is 16 bytes. Then, which is, so we can just analyze the pros and cons of this cache. So it means this cache includes larger blocks. Okay, so which means a single block size is larger. Okay, then what is the benefit? Benefit of this larger block. So we learned that so when the CPU access the cache, then there are there are two results. So one of the result is a hit. Oops. One of the result is hit and or miss, right? And then in order to increase the performance of our computer system, then actually we need to increase the hit rate, right? Obviously, right? So because the cache is faster than memory. And then if we can find the requested block or requested data in the cache more frequently, then we can increase the performance, right? Then what is the benefit of a large block? We may increase the hit rate because of spatial locality. So what is the spatial locality? If a certain data is accessed, then with a high probability, the CPU will access the neighbor blocks. So think about this. This is the cache block size. If the cache block size is larger, then so let us assume that this data is firstly accessed. Then if we just access the array data sequentially, then we will access this data. But because this cache, so if this cache block size is small, then it's when we access the 16 array element, then if a cache block just includes the 4 elements, then this is the 12 hits and 4 misses, okay, for the smaller cache block. But if a larger cache block can include the 16 elements, then we can say that, this is the 15 hit and then 1 miss, right? So benefit of a large block. So the benefit of the large block is that we can exploit the spatial locality. Okay. So actually we will learn about the 3 C's of the cache, like it's the source of cache misses. So actually we can reduce the cold miss. Okay. So we will learn later. So actually, so anyway, so using large cache blocks, so we can exploit the spatial locality. But the large cache block also includes the demerits. So what are demerits? Cache, it's called the cache pollution. So if the cache size is the same, right? Then if we just increase the block size, then the number of blocks is decreased, obviously, right? Okay, because the cache size is the same. So the cache size, is the same, but if we just increase the the block size, then this cache will include the smaller number of blocks, right? So then what's the problem? The problem is that this cache will include obviously a smaller number of blocks, right? So it means it cannot store uh, the smaller number of different data. So for example, so in this example, the cache block can include the 1024 blocks. So which means this cache can store 1024 different data chunks. Okay, but if we just increase the size of a block, so this is the block size is 4 byte, and then so this is the number of a block. And then if we just increase the block size to 16, then if the size of the cache is the same, then the number of block is decreased to 256, right? So right saying. So what does that mean? Using this cache, then we can just store 256 different data chunks. Okay, we cannot store more different blocks in this cache. Okay, so this is the demerit of the cache. So it's cool. So So sometimes so actually I mentioned that using a large block, we can exploit the spatial locality, but actually because of this uh, this cache pollution, the cache pollution is that so cache cannot store the the uh, more different blocks. So some blocks need to be evicted from the cache before it is used. So it's called the cache pollution. So actually, because of cache pollution, the cache hit rate can be decreased. Okay, so also the another demerit is the large miss penalty. The miss penalty means that it's the required clock cycles for handling cache misses. So if the cache miss is encountered, so then we need to allocate this cache block using the new data, right? But in order to allocate the large blocks, then the more clock cycles will be taken, right? This is the cache penalty, cache miss penalty. So if we use a large block, the cache miss penalty can be increased. Okay. So, so actually we need to analyze the pros and cons of the different cache organization. So we need to understand it. Okay. So let's learn about the behavior of CPU for cache miss cases. So in chapter 4, we learned about the CPU architecture, right? And then I mentioned that. So actually, the instruction memory and data memory are level 1 instruction and data caches, right? And then actually, when we learned about this CPU architecture, we did not consider about the cache misses, right? So it means we can always find the requested data in the level on cache, level on instruction cache. So it's the instruction memory, and then also level on data cache. It's the data memory. So for the cache hit, so we assume that for the cache hit, so which means that if we can find the request data in the level on cache, then it takes one cycle, right? Okay, so CPU process normally. That's what we learned in the chapter 4. So it means for the level on instruction cache access or the level on data cache access takes only one cycle. So it's the cache hit case. Then what will happen for cache miss cases? So So we will learn, so this is the CPU, and then, so GPU will access the cache, right? So if the cache, for the cache hit, it's a good case, right? But in the cache miss, then what will happen? We need to access the level 2 cache, right? Or we need to access the memory, right? So we need to access the low level memory hierarchy, okay? Then what's the problem? It will take long time. Okay, so it means for missed cases, in order to access the lower level caches or memory, then it will take many cycles, so more cycles, right? And then these cycles are called as I mentioned, is the cache miss penalty. So cache miss penalty is the additional cycles for handling cache misses. Then what's the problem? So we the CPU accesses level 1 instruction cache or level 2 level 1 instruction data cache to get some data from the cache, right? But if this data is not ready in the cache, then the CPU needs to wait until the data is allocated in the cache, right? So CPU pipeline is stalled. CPU pipelines are stalled, okay? Because it will take more cycles. So for the instruction cache misses, so think about this. So in the instruction fetch stage, the CPU tried to read instruction from the level 1 instruction cache, but this instruction is not found. In this case, the CPU needs to access the level 2 cache, but it will take more cycles. So until the instruction is ready in the level 1 instruction cache, the CPU needs to wait. Okay, so for the cache miss case, it's a level 1, then, oh, it's a miss. Then the CPU needs to access the level 2 cache. But it means for the in the instruction fetch stage, the CPU needs to be stalled. Okay, so because the instruction is not ready. And then if the requested cache block is allocated, then CPU accesses this level 1 instruction cache again, right? Because it's allocated, then the CPU can get the requested instruction from the level 1 cache. Okay. So then so it means it restarts the instruction fetch. Okay. How about the data cache misses? For data cache misses, so for example, it's a load word instruction. Try to access the level 1 data cache, right? But it's cache miss. So the load word is stuck in the memory stage until this data is ready in the level 1 data cache. So because the load word is stuck in this memory stage, the following instructions are also stalled, right? So until the data is ready in the level 1 data cache, the pipelines are stalled. Okay, this is the behavior of cache misses in the CPU. Okay, so this is the cache miss behavior. And then also we need to consider about the write operation. What is the write operation to the cache? So actually for the level 1 instruction cache, the CPU does not write, okay? Because the instruction memory is the read. So CPU just read the instruction from the level 1 instruction cache. But the memory can be updated by store instructions, right? The store instructions updates the data in the memory. So what does that mean? It means when the store instruction is executed, then the store instructions can update the level 1 data cache. So until now, so we just consider the actually read operation, right? So we assume that, oh, this data is requested for read, and then if the data is found, this is a cache hit, and if data is not found, it's just cache misses. But we also need to consider about the write operation. Okay. So let's think about the write hit first. So what is the write hit? Write hit means that, oh, store instruction try to write, like so on, like some immediate x2. So this is the address. So using the address, the store instruction try to write some data to this data memory. Okay, this is a data cache. And then the target block is found in the cache, right? So this is the write hit. Then why do we need to consider about the write operation? So you may think that it's the same to the read operation, right? Well, problem is that the read is okay because we just read the data, which means the memory is not changed. But the write operation is different. Why? Using the write operation, a CPU changes the memory. Then what's the problem? Store instruction, using the store instruction, the write hit means that, oh, the data is found in the cache. Then we can just update the part of data in the cache block. Then what's the problem? The problem is the same data actually was in the Lebanon cache, also memory. So actually they are the same data because the address is the same. But using the store instruction, oh, this data is changed. So what's the problem? Because the address is the same, these data, the data in the cache needs to be identical. So identical to the data in the memory because address is the same, right? But because there are two chunks of data in the different position, the different memory, right? So one of the same data is in the Lebanon cache, and then some same data was in the memory, but only this data is updated. The data in the Lebanon cache is updated. So what's the problem? So it's the same data. So like the variable name is A and A. But so we just update the A with the some value like 10. But the A was 0. The problem is the same variable, but the different data is in the cache and memory. Okay, that can be possible. So that's why. So actually, the write operation is critical. So it's also it's a critical part in the memory, right? And then actually this problem is called the coherence issue. Coherence. Okay. It means the data in cache can be different from the data in the memory. Okay. So actually the CPU can handle this situation differently. The first approach is write through. So write through means that, oh, if the using the store instruction, cache is updated. And then we already know that the same data is in the memory, right? So write through means that CPU also updates the memory immediately. So, oh, it's updated. Then using the same value, the memory block is also updated. So this is the write through policy. Write through policy. Okay, for the write heap. Okay, but what's the problem? So why do we use cache? We use cache because the main memory is slow, right? So it means the read is also slow, but it means also write is slow, right? Write is slow. So problem is, oh, we need to update the memory. So, oh, cache is updated and immediately, so we will update the memory, but it takes cycles. It takes time. So in order to access the slow memory, then the CPU will take more cycles. So this is the example. The base CPI is 1, but 10% of instructions are stored. And then write to the memory takes 100 cycles. Then what's the effective CPI? Okay? For every write, so which means the CPU needs to access slow memory. Okay? Then the effective CPI becomes 11. So you can calculate like this. The 10%, and then it's a cycle, the additional cycle. So effective CPI becomes 11. So what does it mean? So because of a write operation, the CPU performance is slowed down 11 times. Okay. So it's a huge, it's very huge impact, performance impact, right? So it's not good. Actually, if we just consider the performance, so it's actually the conventional, so the write through approach is not good. But we have a solution. If this memory is slow, then we can have additional buffer here. And then this buffer is called the write buffer. So to think about this, so this is the transmitter and then this is the receiver, right? But if the receiver is slow, but we want to transfer data to the slower receiver, right? So in order to solve this problem, then we can have buffer, right? Between the transmitter and receiver. So we can also use the write buffer in this case, right? So it means the request is temporarily stored in this write buffer, and then the the request is given to the memory. So when the request is transferred to the write buffer, then CPU think that, oh, this write operation is done, then CPU can execute another instructions. Okay, so you can use the write buffer. But because it takes time until this write update is reflected to the memory, then the write buffer can cause also the the memory coherence issues. So which means for certain during for several cycles, so for several cycles, the data in level on cache is different from the data in memory. Okay, it can be possible, but the performance is also so critical. So we can solve this issue using the write buffer. Okay, and another policy is write back. Okay, so what is the write back? So this is the CPU, and then this is the level on data cache, and then this is the level 2 or memory. And then let us assume that this is the write heap, okay? And then when the store instruction is executed, then we just update the part of cache block. The write back policy means if the write hit keys, then when the CPU just update the cache block, then this update is just reflected to the cache. Then what's the problem? The problem is, oh, data is different. So this is same A, but the A is different in the cache or memory. But CPU will access, so when the CPU access the A again, then CPU will access level on cache first, right? Then CPU will access the updated value in the cache. So, so A so A was 0, then A is updated by 10, then we just access the A like this, then the CPU can access this value. So even though in the memory the A is still 0 in this case, right? But the A is 10 in the cache. And then CPU will first access the level on cache. So CPU will access the latest value in variable A. So write back policy. The write back policy means that for the write hit keys, the CPU just updates the cache only. Then when this value is updated to the memory, by the write back policy, if this cache block is evicted from the cache, so it can be evicted, right? Because the cache size is small. Then this updated block is reflected to the memory. So it means, oh, this block is evicted. So it's removed from the cache. So what's the problem? The update value is removed. So in this case, this updated value is reflected to the memory in this case. So in the write back policy, the updated cache block is reflected to the memory when this block is evicted from the cache. Okay? So this is the write back policy. So which means the cache block requires the additional control bit, additional flag. So it means this bit needs to indicate whether this block is updated or not, right? And then this bit is called the dirty bit. If the dirty bit is 1, which means that the corresponding cache block is updated in the cache. If the dirty bit is 0, then which means that the corresponding cache block is not updated. So based on the dirty bit, the value of the dirty bit, so if the dirty bit is 0, and then if this cache block is evicted, then it's just evicted. It's removed from the cache, and that's it. But if the dirty bit is 1, which means that cache block is updated in the cache. In this case, if this cache block is evicted from the cache, then this cache block is returned to the memory. So this is the write back policy. Okay. And then, so usually also the commodity CPUs use write back policy. Okay. Usually the CPUs use a write back policy. Okay. And then we also consider the write miss, write miss case. So you may think, oh, why is it so complicated? But usually, in the memory, the write operation is more tricky. Okay, it's more difficult to understand. Okay, because so if we just have a memory, then it's simple, right? So actually, the software guys, actually, it just you handles the register file and memory. So it's a very simple model, right? But in the real hardware, the hardware also includes the cache, right? So that's why the write operation is It's more tricky. Okay, it's more complex. Okay, so how about the write miss? So what is the write miss? So CPU tried to write some data using the store instruction, but the in the cache, the cache does not include the target block. Okay, it is the write miss. So there are also two different approaches for this write miss. Okay, so this is the cache, and then this is the memory. So the first approach is allocate on miss. So it means like the normal cache miss. So it means that the normal cache read miss, when the write miss is encountered, then the cache requests the target data block from the to the memory, and then this block is newly allocated to the cache. Okay, like the normal cache miss. So in this, and then the using the store instruction, the cache block is updated. So this is the allocate on miss. Okay. Another possible policy is the write around. So write the write operation. Write operation just updates the data in the memory. So in this case, for the write miss case, then the CPU bypass the cache and then directly update the data in the memory. So this is the write around policy, right? Okay. So you can also use the different policies for the write miss case. But usually for the write back cache, so it means the commodity CPUs, we use the allocate on miss policy. Why? Because so you so this is the write operation, right? And then if a certain data is written to the memory, so it means updated the memory, then with the high probability, our program will request this data, right? So for example, A was 0, and then we just update this A with the new value. Why? Because we want to use this new value, right? So like the B equal A plus 1. So once the variable is updated, it means usually in the near future, this variable will be also used again. That's how we program the code, right? A certain data is updated, then we will use the same data again. So usually the CPU employs allocate on miss policy. Okay, so which means when the write miss is encountered in the cache, the block is allocated to the cache, and then it's updated. And then this is the write back. Usually, I mentioned that the commodity CPU uses the write back policy. So just the cache is updated. Okay. So write operation is a little bit tricky because we can apply some different policies as a write through or write back policies. For the write hit case, also for the write miss cases, we can apply the write allocate on miss or write around. Okay. So there are different, there can be different write policies to the cache. Okay. So this is some example. Okay. Then so I will just skip this slide because we can firstly understand about the cache performance. Okay, so until this point, so we learned about the cache direct mapped cache, right? The cache organization. So we learned about how the cache miss is handled. So we learned about how the write operation is handled in the cache. So now, so in this part, so we will learn how to measure the cache performance. Also how to improve the cache performance. So why do we need to learn about the performance? Because so based on this performance equation, that we can just analyze why the performance is degraded in by some components, and then we can just make some ideas that can improve the performance, right? That's why we learned about how to measure the performance. Okay, so think about the performance of the cache. So how can we increase the performance? So which factor determines the performance of cache? So think about this. In order to increase the performance, firstly, we need to reduce the cache misses. So which means we need to increase the cache hit rate, right? So we need to reduce the cache misses. And then what is the another factor? So I explained how the CPU handles cache misses. So when the cache miss is encountered, then CPU needs to wait until the request data is allocated to the cache. Now, what is this? This is the miss penalty. So another approach is to reduce the miss penalty. Okay. So you can think like this. So in order to improve the performance of the cache, then firstly, we need to reduce the cache miss rate. So we need to reduce the number of cache misses. And also we need to reduce the miss penalty. Then you can think like this, okay, for the cache performance. Okay, so the CPU. So firstly, we can define the memory store cycle. Okay, so what is the memory store cycle? So because of cache misses, the CPU needs to wait, right? For additional cycles. So this is called the memory store cycle. So which means the pipeline stores because of cache misses. So how can we calculate these memory store cycles? Okay, a program also includes the memory instructions. Also, we need to no, the CPU needs to access instruction memory in order to fetch instructions. So there are two different memory accesses. So firstly, the memory accesses for fetching instructions. And then the second memory access is the type of memory access is the memory access is by load and store instructions. Okay, so memory access includes these two different types of accesses, the memory accesses. So our program, so actually uh, every instruction needs to be fetched from the memory. So which means all instructions also includes memory accesses. And then additionally, the load store instructions. Load store instructions also includes the memory accesses. Okay. So we can just identify the number of memory accesses per program, and then it's multiplied by miss rate and then miss penalty. So miss penalty is the additional cycles for handling cache misses. Okay, we can calculate the memory store cycles like this. Okay, so this is the some equation that defines the additional cycles by cache misses. Okay, so in this equation, you can find that this part we cannot change it. So which means this part is determined by software, right? But this part is determined by cache organization. Okay, so actually cache needs to, in order to improve the performance, then we need to tackle these factors, miss rate and miss penalty. That's what I mentioned previously, right? So let's see the example. So this is the configuration. The instruction cache miss rate is just 2%, and then data cache miss rate is the 4%, and then miss penalty is 100 cycles. Okay, and then base CPI. So which means that if we just ignore the cache misses, then the base CPI is 2. Okay, and then let us assume that load and store instructions occupy 36% of all instructions. Right, this is the given condition. Then we need to calculate the performance degradation by cache misses. So we can calculate the miss cycles per instruction. Okay. So, and then as I mentioned, every instruction accesses instruction cache, right? So the ratio is 1, okay? 100% of instructions accesses instruction cache. So the additional cycles per instruction because of the instruction cache misses is the 2% miss rate multiplied by miss penalty. It's 100 cycles. Then it's 2. What does that mean? For every instruction, 2 cycles are added because of instruction cache misses. Okay. How about the D cache? Data cache is accessed by only memory instructions. And then also, this is the percentage of memory instructions. So we just use this information. So 0.36 multiplied by cache miss rate for the data cache is 4%. Okay, and then miss penalty. So 1.44. Okay. So actually, what is the actual CPI by cache misses? The ideal CPI 2 plus the the CPI, the increased CPI by instruction cache misses, it's 2, and then 1.44. So total CPI is 5.44. And then if we just compare the performance with the ideal CPU, then ideal CPU is 2.7 times faster than the non-ideal CPU. Okay, so if we just consider, so this is the very simplified, very simple model. But if we just consider the cache misses in the instruction cache or data cache, then which means the non-ideal CPU is 2.72 times slower than the ideal CPU. And then this is very huge, right? So that's so, and then it actually this value is very uh, very small value. So which means that it's very positive configuration, positive configuration. So usually the miss penalty is larger than the 100 cycles. The miss rate, it can it is different by the applications, right? Because the miss rate is also influenced by the access patterns of applications. But anyway, so this miss penalty is very small. It's 100 cycle. But using very simple configuration, so like using very simple scenario, but we can find that the CPU slows down dramatically. That's why the performance of a memory system is very critical, as I mentioned. It's very critical for the performance of a computer system. Okay, so so this is so using this information, that we can just estimate the how the uh, CPUs can slow down because of cache misses. Okay, and then we can define some another performance metric of cache, and then this is called the average memory access time. So this average memory access time is called the AMAT, average memory access time. Okay, so average memory access time represents the number of average cycles for accessing memory. So what does that mean? So it's the same saying, average memory access time. So as I mentioned, when the instruction is executed, these instructions access memory. So for instruction fetch, every instruction accesses memory. Also, the memory instructions access access data memory, so data cache, right? So average memory access time is defines represent how many cycles are taken for accessing memory. So this is the averaged value. Okay. So for the ideal case, AMAT is the same to the heat time. So in chapter 4, so we did not consider about the cache misses. Then what is the heat time? One cycle, right? Because for instruction fetch or it also when load or store instructions access data memory, then we assume that this stage will be complete within one cycle. So heat time is one cycle. So this is the average memory access time for the ideal CPU, okay, as ideal cache. But because of cache misses, this amount of time is increased. Okay, so we can calculate the miss rate multiplied by miss penalty. Okay, so this is this is the averaged value, right? So we can just calculate the so miss penalty. So this is additional cycles for handling misses, and then miss rate, and then based on this equation, that we can compute the average memory access time. Okay, so amen. So this is the example. So CPU with 1 nanosecond clock. So clock period is 1 nanosecond, and then heat time is the 1 cycle, and the miss penalty is 20 cycles, and then I cache miss rate is the 5%. Then based on this information, then we can calculate the AMAT, so which means the average access time for accessing instruction cache or instruction memory. So hit time is the 1 cycle, and then miss penalty is 20 cycles here, and the miss rate is here. So it's a 2 nanosecond. Okay, this is the average memory access time for instruction cache. Okay, so based on this one, so we learned how the caches influence the performance of CPU, right? So until chapter 4, we did not consider about the cache misses, but when we consider the cache misses, then we can calculate, we can figure out that the performance can be dramatically degraded. Okay, so then how can we improve the performance? So if we just see the AMAT equation, then is heat time, and then what plus, and then miss rate multiply miss penalty. So as I mentioned, we need to reduce the miss rate or miss penalty. But this penalty is determined by the performance of memory. So it means the latency, okay? Latency of the memory, and then also the clock frequency of CPU. So which means if the CPU clock frequency is very high, but if the memory latency is the same, then this penalty is increased, right? Obviously, right? So we can consider some impact by CPU or the memory. Okay. Okay. So we have just 5 minutes, but let me briefly explain about the associativity of cache. So until this point, we learned that the performance by cache is determined by miss rate and miss penalty. But this miss penalty is determined by CPU performance. So it means the CPU clock frequency and the latency of memory, right? And then latency of memory is some native characteristics, right? We cannot change it, right? Because it is determined by the performance, so speed, the performance of, so speed, the latency of memory is determined by the circuit design and semiconductor technology, okay? But miss rate. So as I mentioned, the miss rate is also influenced by workload. So it means application, because the access patterns of applications determine miss rate. But this miss rate is also influenced by cache organization. So for example, I explained about the size of a cache block, right? And then I mentioned that if we just increase the size of a cache block, then we can we can utilize the spatial locality, right? So it means we can, not always, but we may reduce the miss rate. So cache organization also influences miss rate, right? Then let's learn how to reduce the miss rate of the cache. And then it is determined by associativity of cache. So, associativity. So we learned that when the cache index is determined, then we just store one cache block. Then what's the problem? So problem is that we want so let's see this some so scenario. Inside of the for iteration loop, we firstly access the variable A and then variable B, right? But let us assume that so this the index of the cache is determined by some index field in the address, right? The part of address bit. Then let us assume that A and B have the same index. Then what's the problem? Oh, this cache can include only one cache block by this index value. Firstly, A is requested, then A is allocated in the cache. And the next, the B is requested. Or B is requested, but the cache does not have a B, but the target cache block is already occupied by A. So in this case, the A is evicted from the cache and then B is allocated. But this is the iteration loop. A will be requested again. So what will happen? Oh, A is not found. A is allocated and then B is evicted. Oh, and then B is requested again. B is allocated. A is evicted. What's the problem? If we just see this iteration loop, then we can observe locality, right? Temporal locality. The same A and B are requested again and again. But because of the limitations of cache, A and B are allocated, evicted, allocated, evicted. So we cannot utilize the cache effectively. Then what's the problem? Problem is that if the cache index is the same, only one block can be stored, right? This is the problem. And how can we solve this problem? For the same index, if cache includes the multiple blocks, then we can avoid this situation, this scenario, right? So this is called the cache associativity. So cache associativity represents that for the same index, the cache can include the multiple blocks. Okay, so we will learn about the cache associativity in the next class. So I will record the video and I will post the recorded video for upcoming 4 classes. Okay, so thank you for attention. Then good luck for the final exam.